Hello, everyone. Thank you for attending today's webinar, which we're going to talk about some of the advantages of using FeeFlow for your groundwater modeling for flow and contaminant transport. My name is Nilson Giger. I am with Water Service and Technologies, and this webinar is put in partnership with DHI, which provided a lot of the material I'm going to present, as well as Hydroinfo, which is the distributor of DHI products in Brazil.
Too much water, too little water. Your mine operation demands a complete understanding of water resources. Water Service and Technologies team of water specialists support mines with a full range of technical services that address water challenges.
Our clients rely on our expertise in advanced environmental data management and hydrogeological modeling to better understand water concerns. We provide a big picture view of water balances and develop mitigation techniques to address water surpluses or shortages in an environmentally friendly and sustainable manner. First, let's talk a little bit of history of FeeFlow. The FeeFlow has a long history. It's nice because it keeps being developed. It all started in 1979 with these three individuals, Stefan Kaden, Hans Dirsch, and Ingo Mitjos. And it started the Academy of Science of Berlin. It was a time where East Germany was still active. Each one of the three, one was her professor, the other one was the brain behind programming and developing the math of FeeFlow, and the other one was more commercial. It came in 1989 and Berlin Wall went down, and these three individuals took FeeFlow out of the Academy of Science and started their private company, WASI, based in Berlin. At the same time, I had just started Waterloo Hydrogeologic, and this was our first website. I was very proud of it. Now it's ugly. But we had a few software packages. One of them was Visual ModFlow, which is based on the popular package ModFlow. But even though we were the developers and resellers, of course, of Visual ModFlow, we felt the need to have a more advanced package, both for our consulting projects, as well as to our clients that demanded software packages that Visual ModFlow or what ModFlow based package could not do. And that's what we're going to talk a little bit today. So up to this day, I still think there is room for both. There are some people that prefer or some clients that need to be ModFlow, the models. Some clients don't care about being ModFlow. And some projects, maybe quick, easy applications, people can use ModFlow based packages. And for more complex sites, one should use FeeFlow. So I think there is room and need for both types of packages even to this date. It came at the time in 1991, Berlin Wall just came down. I had the chance to meet these three individuals and went to visit them in Germany and made a deal. So Waterloo Hydrologic translated from German to English and brought from Unix to Windows. And in exchange, we became sole distributor outside German-speaking countries, basically Germany and Austria, for the whole world, and that lasts for almost 20 years. We were distributing, so that shows that it has room for both, and the arrangement worked very well for both parties. It came 2007, the AGI was sold to WASI, Waterloo Hydrologic was sold to Schlumberger, and then FeeFlow became part of the AGI portfolio, which has a whole variety for all aspects of water. It has software packages that are very powerful, and it was a nice fit to have such a powerful groundwater model into their portfolio. So up to this date, FeeFlow is being developed, strongly supported, and it's very important when choosing a package to know that the package will be there for years to come. So every year they have great news on developments of FeeFlow. Now let's just start with some basic concept. Our groundwater flow model is based on Darcy's law, where basically it says the flux is directly proportional to the grade. Very easy law, and the proportionality constant is the hydraulic conductivity. From that, one can derive the groundwater flow equation based on a mass balance. So whatever comes in minus whatever comes out has to be equal whatever is changing in storage. Now, if I bring that to a very small site, a very small volume, so whatever comes in and whatever comes out is whatever comes in plus a delta difference. So if I replace now Q by Darcy's law, I get the three-dimensional saturated groundwater flow equation, which needs to solve discretization in all directions, X, Y, Z. It needs this parameter, which is the hydraulic conductivity. It needs storage coefficient. And here it's whatever has coming from outside or being pumped from the cell itself. So sinks and sources outside. And needs boundary conditions as any solution of differential equations do. Now this, we say it's an easy system to model because it's all based on porous medium, basically Darcy's law, and the principal directions are aligned with the coordinate axis. So we have three components of K, Kx, Ky, Kz. For contaminant transport, we have a different set of equations, whatever comes in and out by dispersion, plus whatever comes in and out brought by the advection of water, plus any source or sink, basically reactions that occur inside that cell, is equal to the change of mass stored in that cell. Solution methods for those can be either analytical or numerical. Analytical, there are some well-known analytical solutions. TIES is one of them that we use for determining, for example, transmissivity for pumping tests. That assumes that the aquifer is infinite, homogeneous, and totally horizontal, the TIES solution. As with any analytical solution, it does not allow heterogeneities because it's basically solving a continuous system. It's like it's solving one cell only. The other solution that's well known is for contaminant transport, Domenico. It became very popular because Rebecca, risk-based correct reaction, it uses that as a base. But if you want to have any heterogeneity or partial penetration of a river or things like that, then you need to go numerical. And numerical models, the most common numerical methods used are finite difference, finite elements, and finite volumes. And the most popular software packages used these days are either ModFlow based or FeeFlow is running basically alone in this commercial portfolio for graphical user interfaces. ModFlow based packages, there are several of them: Model Muse, Visual ModFlow, GMS, Groundwater Vistas, and FeeFlow, the finite element basically alone. A couple of packages for ModFlow. Model Muse is popular because it's free. It is developed by USGS. It does not support the latest version of ModFlow, the unstructured grid, but it does support FAST and Sutra, which are two other powerful models in terms of equations. It uses traditional finite difference or the local grid refinement, nested grid, basically. Now, it's popular and it's nice to teach as a teaching tool, but the graphical interface is kind of crude, so it's still not very powerful to use. Visual ModFlow is another popular package. Visual ModFlow Classic used to have only finite difference. Now the Flex, it has one differentiation because you can build the conceptual model right in the graphical interface of Visual ModFlow Flex, and then it's totally grid independent. So once you have your conceptual model, you can put traditional finite difference, you can put Voronoi unstructured grid for the ModFlow. So it becomes very nice, but has the limitations that we are going to see intrinsic of ModFlow. We're going to see some of these limitations, which is overcome by FeeFlow. FeeFlow is developed by DHI, use finite elements. It has the advantage of being able to better represent complex geology, mainly now with unstructured grids. You can individually represent faults, structures, karst features, directional wells. It has built-in unsaturated zone and density-dependent flow and heat as well. If you're going to use for box type models or gas station types models in terms of flow, basically you don't gain much. It's all interface that you are used to. And you don't gain much or lose much by using any of these packages, both in terms of time as well as accuracy. However, there are modeling challenges where you need something more powerful. So if you are worried about contaminant going from the surface, going down through the unsaturated zone in 3D and then reaching the water table and moving, that's a challenge. If you have variable density caused by either high concentration of some contaminant or salt water from sea, or by temperature changes. If you have highly folded areas where the principal directions can change spatially, so if you have a syncline, then you have different directions of the principal hydraulic conductivity directions. If you have individual faults that you want to represent, if you are in a karstic feature, a karstic zone, if you have a complex geology and you want to have a highly accurate representation, and if you want to integrate with a geological model package, then those are things that FeeFlow can offer you, because those are systems more difficult to simulate. So let's see, the one advantage is if you have principal directions that are not aligned with coordinate system. So you may have areas that it's easier for the groundwater, even if the gradient is from horizontal, groundwater will go down a little bit because of component of the geology. Here, it may go down in a different way. So if you have the principal directions of K not coinciding with the axis, and it's sometimes impossible, if you have a syncline, you cannot coincide in all places, not even rotating the grid. Then what happens is that the equation itself, it doesn't have 3 components, kx, ky, kz anymore, it has 9 components. The k becomes a tensor. FeeFlow allows you to have, in every element, you can have a different direction for k. And then you don't call it kx, ky, kz, it's k1, k2, k3, because those are directions that can change, not coinciding with x, y, z. You provide those 3, and you provide the 3 angles, and then it can solve things like that. It also allows you to represent individual fractures. And in the individual fractures, it may not use Darcy's law, where the flux is directly proportional to the gradient by one single value, which is hydraulic conductivity, K dH dx. In this cubic law, it's still the flow or flux is directly proportional to the gradient. However, instead of K, it uses something that is related to the aperture of the fracture, to the rugosity of the fracture and the viscosity. It's called the cubic law, for example. If you have flowing karst channel, it can be an open channel of a cave, and then you have a river inside the cave. Then you can use money, can use Darcy's Weisbau for closed pipes or ducts. So you can represent that in FeeFlow as well. Couple of examples, a tailing dam, which usually mines are located, unless it's maybe a coal mine or things that are taking ore from stratified areas. Usually mines are in a very complex geology zone, and they put the mine tailings close to the mine. So the mine tailings are in high complex geology areas, and the models are used as decision support tool and should reflect geology as close as possible. So you have the tailing, you have a dam, and you want to see the effect of this future tailing in this area. So if you have a tailing here, and then the principal directions do not correspond with the horizontal and vertical. And just conceptually, what can happen is, if you use ModFlow based model, which allows only this portion, you may arrive at this conclusion. This is the location of the water table. Yes, this creek may be impacted, but this creek will not be impacted. Now, just by changing the principal directions, you may have a totally different effect. The water table is lower and the impact is much widespread. So then you have to play with this, and that effect you would not see unless you use these principal directions. Another factor is if you have a low K zone here, for example, if you don't represent this low K, which maybe is just an intrusion that may be 2 or 5 meters thick, not very thick comparing to the whole thing, but that particular layer is what makes a difference in the water table. So you have a well here and you have the water in a elevation, high elevation. You go 20 meters away and put a well here, boom, the water drops. This big drop is caused by this basically acting as a dam, underground dam. And if you don't have the ability to represent that, you may have gaps. So if you use traditional layer like ModFlow and you have to represent this as a staircase, there may be voids in between that the water flows through, and then your average water table will be somewhere here. You're never able to calibrate this level and this level at the same time. This is a practical example where we saw that. This is here in Brazil, in this iron ore zone of Minas Gerais. And there is one formation here, which is an aquiclude, called this Batatal formation. And in this case, what we want to study is a particular operation, industrial operation here, if it was affecting some springs on this side or not, or if the springs were getting dry because they had a 3-year span of low precipitation. We applied FeeFlow for that. Interesting in this case is that we have done some pumping tests. This is one example of one where clearly you see that not only vertically you have an isotropy, but in this case, which is not that common, but you have also Kx different than Ky, anisotropy. So you have a much higher drawdown in this direction than in the direction towards the spring that we were studying. And that ability to represent these different Kx in plan view as well, in different angles, depending on where you are in the model, is also important. We have developed a model in Leapfrog, as we do a lot of times this day, either using GeoModeler or Leapfrog. Those are the two main ones we use for geological models. We developed Leapfrog, exported the grid to FeeFlow, and we built the Leapfrog because we did some structure mapping and geological sections and surface geological maps. We calibrated this model, and this is the end result. This formation being well represented, it allowed to have this water level calibrated here, because here the water level was high, all of a sudden was very low. And that was very important to calculate. Otherwise, we would see a potential impact in the spring that may not be there, because it would just represent an average water table here, and it would lower the water table more than it is lower in nature. Another example, importance of considering individual fractures and structure, which FeeFlow allows you to do. If you do a Darcy's Law model, you have one flow system. Now, if you consider the faults, which clearly is identified here, and you consider these individual faults, you end up with a totally different pathways. And then in this case, for example, it had a spring, a natural spring coming here, and you could not calibrate unless you would consider this system of fractures. In this case, FeeFlow allows you to simulate individual faults and structures. And this is possible via these discrete features. FeeFlow allows a number of different types of elements. The traditional one is this prismatic element. So basically it's triangle in plan view and then vertical faces. It allows quadrilateral. It allows, most recently, 3 or 4 years ago, it started to allow tetrahedral elements, which made it very flexible, but also allows plane elements. So that plane element, you can represent individual faults by representing plane elements, because FeeFlow allows you to mix and match. You can have tetrahedral, or you can have prismatic and plane elements, and in between two prismatic elements, you have a plane element. So for example, you have Darcy's Law occurring as a porous media in your groundwater. Once it hits this plane element, you may have a different cubic law, for example, so that the contaminant, it goes as a porous media. Once it hits the fracture, boom, it moves much faster. So it allows you to mix plane elements with 3D elements. It allows you to mix line elements that can represent, for example, inclined wells with 3D elements. And you can also mix, for example, most of your model, you represent prismatic because it's still easier to work in the interface with layered models than totally not structured model. So a good strategy is to represent tetrahedral or prismatic elements everywhere, but close to where you have inclined fault you want to represent, you change to tetrahedral, so you can mix and match. In these individual elements, you can have, in any element basically, you can have this Darcy's law, so flux is proportional to gradients, and there is one constant, K value. So that one you can use inside a line element as well, because you can still say in this line element, it's proportional, and I assume one constant parameter called K that may be, for example, higher or maybe lower K than your porous media, or higher K. So once the water hits there, it meets that higher K and deviates to that, but inside that plane only. If you want another type of equation, you say, instead of a K value that I'm going to take from the air, let's say, or use as a sensitivity parameter or calibration if I have the data, I'm going to use a K value. The formula is still the same, but I'm going to use a K value where it uses the hydraulic radius and the viscosity and the aperture of the fracture. Now, you may feel it's more precise, but it ends up that you have to pull from there the aperture and the hydraulic radius of the fracture. So a lot of times we end up using Darcy's law inside fracture just because it's as precise as this one, Hagen-Poiseuille, if you don't have the parameters of aperture and rugosity. But it allows you to use this Hagen-Poiseuille. That's a nice one, not for fractures, maybe specifically, but if you have closed pipes, you put a 1G element, but it's an inclined well that you have there, and you can use then this formula and give the hydraulic radius of different shapes and use that formula. You can use money strictly as well. For example, if you have karst features and you have open channels that you want to represent, you could use that as well. This is in the FeeFlow white papers that's available freely on the internet, and you can read all the math about it. One example that I'm putting today, because it's showing how advanced was already FeeFlow when we first got them at Waterloo. This was 20 years ago, but still a nice example of bauxite mining in Jamaica. And that was a site that was full of faults, and there was basically a tailing pond here. It was not even a pond, it's not a dam, it was just a lake that they would put the tailing here. And the contaminant started to migrate. This was 1,500 meters. This is one side of the sea of Jamaica. This is the other side of the sea in Jamaica. The island is stretching this way. And the contaminants start to move all sides. It was a mess. And start to arrive in a city here and in a city here, or it was about to arrive. So we were commissioned to do this modeling. The fractures, as it's common, they kind of close down with depth. So up after a certain depth, the fractures are closed. So we added this grid and these individual fractures here. There was one main fracture here, and the other ones were not as important. So as we went down, the number of fractures started to decrease, and then it remained only that, and then in the lower layers, there was no fracture represented. We used some wells and some boundary conditions, basically the Caribbean and the other sea here. Did some calibration with the few data we had. And this is one scenario where we were doing sensitivity analysis for the K zone. So if we have lower K for the faults, that means that the flow in the porous media prevails more than in the fracture, or flow in the fracture does not prevail as much on top of the porous media. So the plume is kind of more widespread. With higher hydraulic conductivity in the faults, the plume moving much faster and much more concentrated in these faults. So we had to do a sensitivity analysis and propose some locations for monitoring wells to see what would be good. And in this case, it was very important the feature of FeeFlow to consider density, because the bauxite is high concentration of sodium, and it was 120,000 ppm. Seawater is 35,000. So it was highly dense. And therefore the plume not only spread, they had done some previous model without a density dependent model, FeeFlow, mod flow based, and they could not represent the fact that the plume was going 300 meters down instead of actually being on the surface. This is one example we have done in Peru, where they have this dam that it was built here. This dam has 3 tunnels that are more or less here and discharge here. That is to have the water flow through the tunnels. The water doesn't go through the spill. It goes through the tunnels, the excess water, and comes here. There is one small tunnel, a smaller tunnel, that is used for the generation of electricity. So this tunnel goes directly from here to the powerhouse down there. But also below that, there is deviation tunnel that was used during the construction. It's closed now, but there is a road tunnel as well. And the problem there was that they were losing too much water from this zone to the lower zone. Basically, it was going to the part of the deviation tunnel that was not plugged. So the water was losing from here to here, too much. And it was starting to go in the road tunnel as well. With that, they had economic loss, because by losing the water, then the water available for electricity was not as much as it could. So they want to investigate what would take to be able to grout, if it was worth the effort to grout this tunnel at different levels. So basically play with the hydraulic conductivity of this grouting, so that we see how much effect it would be in the loss of the tunnel. So they select these areas where they would go here and inject cement into these zones. If they inject more cement, they decrease the hydraulic conductivity, but the cost increases geometrically. So if you grout twice more dense, you spend more than twice. So they want to grout this. They have this hydroelectric tunnel, and they have this road tunnel. Here is the area where this deviation tunnel is plugged, but here it was open. So water is flowing from here to here. So we represented that in FeeFlow. We put boundary conditions equal to the water level at this side and just seepage nodes on the other side. We represent the tunnels inside the grid of FeeFlow, all of them. And the reason why the tunnel was leaking is because there is a higher fracture rock in this zone. So the hydraulic conductivity of the rock is higher on this yellow zone than in the rest. And we presented them with a very low hydraulic conductivity. So we put the higher K zone here, the tunnels, played with different levels of grouting, and those are the mesh with the tunnels. And the results, in one section here, heads in a plane. And here it's nice, this example, because it does show, okay, here is saturated because tunnels are full of water. The tunnel of the electric dam is above this tunnel. So this tunnel is losing water. That's where the flow in the electric dam tunnel would decrease, because it was losing directly to the tunnels below. And here is the car tunnel, the road tunnel. And you can see the white line around it. That shows that it can represent the unsaturated zone below the saturated zone, which is a nice feature. So we played with different K values and how much grouting, and say, okay, below a certain point, it's not worth, because you're not going to have a significant reduction in the discharge from the tunnel. So these two scenarios would spend more on grouting, but doesn't change significantly. They use that to calculate their grouting. Now, the unsaturated zone. Unsaturated zone, just to remind, whatever is below the water table, you have a constant saturation, which is equal to the total porosity. You cannot put more water than the total porosity. Above the water table, you have saturation that decreases with height, unless it rains here, but in equilibrium, it decreases with height, and it decreases depending on the type of soil. It decreases faster or slower. You have one zone here that basically the soil is saturated, but it's already here, it's negative pressure. So the plant, to get water from the soil, it has to apply a suction. So it's negative pressure. It's basically negative pressure, but already saturated. That's the capillary fringe. The size of the capillary fringe depends on the size of the pores. And you have this relationship between saturation and negative pressure for each type of soil. Remembering Darcy's law, flow is directly proportional, and this Ks is the saturated hydraulic conductivity, depending on the material. Now, remembering that whatever shows here, hydraulic head, it has two components, pressure plus elevation. FeeFlow always work with pressure and elevation. So it always shows you pressure. If you have two outputs, I want to see heads, I want to see pressure. You can always see pressure because it calculates based using these two components. Now, replacing age by pressure, you have the saturation versus pressure. You also have another relationship, which is hydraulic conductivity versus saturation. If you have fully saturated soil, then the hydraulic conductivity is constant. It's equal saturated hydraulic conductivity. As the soil starts to get dry, hydraulic conductivity starts to decrease because basically the area where the water is flowing decreases. So it's more difficult for the water to pass, hydraulic conductivity decrease. So you have the relationship between hydraulic conductivity and saturation. Remembering groundwater flow equation, 3D, we just saw it, whatever comes in and out is equal to, but now at the unsaturated zone, K is not a constant anymore. K is a function of saturation, saturation function of pressure, therefore K is a function of pressure. As pressure is part of age, I have a non-linearity because I have a parameter that depends on the solution. Now, in the unsaturated zone, what's the difference of storage? Is the difference in saturation. In order to solve Richard's equation, FeeFlow needs to have the relationship between hydraulic conductivity and saturation, between pressure and saturation. It gives you a few options. It gives you the option of using the well-known Van Genuchten relationship, which he did thousands of experiments, and depending on the type of soil, it provided a fitting parameter, which the standard Van Genuchten is just two parameters, alpha, which is the inverse of the height of the capillary fringe, and this parameter, fitting parameter n. If it's modified Van Genuchten, it needs two more, but basically it's a fitting equation. But the nice thing about Van Genuchten is that it published for thousands of different variations of soil the suggested alpha and n. So it's very well used. Brooks and Cotto, it's an older one. It was used mainly for the oil industry. Haverkamp is also a Dutch one. Or you can have your own data. If you have done experiments, you just put your data and does a spline calculation for you. Example of this application was done in a coal mine here in Brazil as well, where they would strip out this area, and we did a FeeFlow model for this area here outside. They would strip out the white zone here. So we did this FeeFlow model, very easy because it was just a 5-meter thick layer of coal that they would strip out. And the result is a cross-section here. The nice thing is that we can clearly see one possibility of FeeFlow. It calculated, this is pre-stripping. It calculates that it had perched water table on top of the coal, and then a lower water table. And we thought that would never be able to calibrate because they had wells where the water table was hit at 5 meters, and then just 30 centimeters from it, a deeper well, the water table would be at 35 meters. And FeeFlow was able to nicely calibrate and represent this. And they had places where the well was just fully open, and then it would be an average or whatever. And it was rewarding to see FeeFlow representing that, which you can never do in ModFlow because it only represents one water table. Applications, water supply wells can capture zone, well field, contaminant risk analysis. Also, it has a powerful equation editor. Whoever use ModFlow, use RT3D. RT3D does not allow you to edit the equation. In FeeFlow, you have an equation editor right there. But if you want to also have reactive transport or chemical equilibrium, it has a connection to FreakC through this routine called PyChem, where then it can have fully reactive transport. Variable density, it's very useful feature. It can be used either for seawater intrusion, for lithium mining, which DHI is doing a lot of consulting on that, and so on. And the density dependent flow is basically what happens there is that we use hydraulic conductivity, but hydraulic conductivity is assuming fresh water. Really, it has one component that is totally dependent on the porous medium, but there is one component that's depending on the fluid. So the same porous medium, if you pass honey or water, you have different relationships. So if you are in a dense dependent flow, you have to use with this formulation because the density is varying cell by cell. Also the viscosity. Density in FeeFlow, it's easy to change. You just change the settings that the relationship between concentration and density is not zero. Zero means that independent of the concentration, the density will be the same, equals 1. But if you change that ratio, as FeeFlow calculates a concentration in a certain cell, it changes the density. It also changes the viscosity. So you can add this, that the viscosity of the seawater is higher than the viscosity of fresh water. It can be linear, but also it can be non-linear. For example, for lithium, maybe the concentration is so high that this linearity doesn't keep growing forever. It has a more exponential shape. It can also calculate heat. So the density can change according to the temperature as well. So it becomes less dense when it's hotter. And FeeFlow then use a more complicated equation to calculate heat or density-dependent flow. An example we did here as well, it's a harbor. And in this case, they tried to put some barriers, injection barriers, to contain the saltwater intrusion of this area here, because they had some pumping wells in the middle and the saltwater intrusion was happening there. So we did a FeeFlow, we did a calibration for 10 years of data that they had in terms of both concentration and levels, according to the wells that they would implement at the time. These are the supply wells that they were using, the saltwater intrusion happening in this lower zone, which is higher K, is going faster than in these other zones. And they were predicting that it would arrive at their wells. So they did this injection barrier and hired us after the fact to check whether it would work. And we did that simulation with FeeFlow. Heat transfer can also have several applications. For example, for pump heat pump, borehole heat exchange, etc. Or it can have, this one is one case in Brazil where it's not a volcano, but it rains here and there is a high geothermal ratio, so the water goes down and comes up. And there are some hot springs, which is very popular, but then they started to overpump water in this zone here for hotels, and the water started to be cooler and cooler, so the hotel association hired to do a FeeFlow, seeing how much they would pump sustainably so that they don't cool out the water as much. And that was done and published in FeeFlow. Finally, Unstructured grid, which was one of the latest advances of FeeFlow, actually since version 7, now they're in 7.3, and they allowed to then start to use tetrahedral mesh, and that becomes very powerful. Traditionally, FeeFlow was used as a layer grid mesh, which graphically becomes easier to work, but now with unstructured mesh, basically you can have triangles from plane or from in any view. And that allows a lot of flexibility in representing geology, representing faults like that with this on location, or inclined faults. Instead of being on a staircase, you can represent like that. An example, if you have open pit and you want to see the dewatering, one can do layered mesh or unstructured mesh, representing then the pit on a structured mesh. And this one was done by Robin Dufour from DHI Peru. And he had a chance to do a model in 2016 or in 2012 using a standard layer mesh. And then he revisited this model and have done in unstructured mesh. And he was able to do a bigger model. In fact, they were not even the same size, but a bigger model with 400,000 nodes instead of 1.6 million nodes. And every run, it was 5 times faster than the previous model. So there is a big advantage, not only representing much better the geology, but also in terms of saving the number of nodes and therefore time. To finalize, some recommended bibliography. This is the Bible for FeeFlow. It is a book that can be bought by Springer, and they have everything you want to know about the math behind finite element and the implementation into FeeFlow. It was written by Dr. Hans Diersch, the original developer of FeeFlow. This applied groundwater has a nice chapter on finite element as well, and it compares advantages or disadvantages of mod flow based models. This one in particular is a cover visual mod flow. Mod flow and FeeFlow, it has a nice chapter on it as well. This one is for one that deals with remediation. It has particular applications of transport modeling. If you want to know more how to represent individual fractures and what parameters to use for rugosity and so on, there is this characterization of and modeling of fracture rock written in Canada. And then some guidelines, which always people ask, how do I review a modeling report? How do I write a modeling report? So there are a couple of guidelines, one from USGS, which is very popular. This one from Australia is more recent, and it's nice because it's focused a lot on mining areas with complex geology. Thank you very much, and the contacts are on the screen, so if you have any further questions, you can contact me later. We are available to discuss with you. Thank you very much.